Okay guys, for this video we're going to do a quick overview of how the periodic table works. I will post a copy of this exact version of the periodic table on OnCourse for you to print off and use during any quiz or exam. I also recommend taking them to lab. They're useful there too. Okay, so let's talk a little bit about the periodic table. So a slight bit of history here, I'll try to be quick. The periodic table is a somewhat recent invention, I guess. Basically, before the periodic table, which was invented in the 1830s, let's just say 1830, okay, approximately. What happened was that everybody just kept a list of all the elements that they've ever heard of and all the information about them. But unfortunately, they tended to keep alphabetical lists, which, as you are probably aware, the periodic table is not an alphabetical order. Okay, or if you just look at the periodic table, you'll see that it's not an alphabetical order. Okay, and the problem is that every country had different names for the elements, so the order changed. So this guy named Dmitry Mendeleev, a Russian chemist, if you ever look up pictures of him, he looks like some evil wizard from Harry Potter. He basically organized the known elements based off physical property rather than name. So what he did was he basically still made a list. He organized elements by properties. So what he did was he listed them by weight. The lighter elements first, the heavier elements later. Which, if we look at these numbers, the little decimal numbers, we see it's 1, 4, almost 7, 9. It's still approximately in that order, okay? And then what he found was that throughout the list, he would see, like, every once in a while, you'd have ones that formed the same charges or form the same types of compounds. So the idea is, so he organized it by properties, which would be mass in this case. And then what he did was he made vertical columns with similar properties. So this is, properties. This would be other properties like charge, color, texture, metal versus non-metal, stuff like that. Okay, and that literally laid out the groundwork for how our periodic table is now. Now we organize them by atomic number, so it's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, whatever. Okay, the atomic numbers. There are a few, and for the most part, the masses also increase in the same order. There's a few exceptions. Let's see if I can find one. Okay, so iron is 55.8, cobalt is 58.9, and then nickel is 58.7. So a slight drop there, but otherwise, for the most part, they just get bigger as you go up. So not drastically different than what Mendeleev said. Okay, and then things that are in the same column tend to have the same properties. So anything in column 1, they tend to form similar charges. They tend to react the same way, form the same types of compounds. They all tend to explode if you throw them in water. If you look them up on YouTube, maybe I can post a video. There's all sorts of fun videos where people throw these in water and they just pretty much catch on fire and explode. Okay, but similarly, anything in the same column have similar properties. So like copper, silver, gold, they don't oxidize very well. In other words, they don't get corroded, and then they have low melting points. You can easily heat them, and they're very soft metals. You can make them into jewelry. Okay. Things like helium, neon, argon, krypton, xenon, radon. These are the noble gases. They don't form compounds. They're really they don't form charges. They're just super neutral. They just sit there doing nothing. Okay, these are the halogens, fluorine, chlorine, bromine, iodine. They're all super toxic. They all form diatoms. Basically, they bond up together, so this doesn't exist as F in nature. It exists as F2, so 2 fluorines come together, 2 chlorines come together, 2 bromines, 2 iodines. Okay, but the idea is things in the same column, these all form -1 charges. They all kind of form the same types of stuff. Okay, so this basic idea of how this works was set in like 1830. Okay, so we talked about isotopes in the last video. I want to mention where these little decimally numbers come from. Okay, so for oxygen, 15.9994. Okay, or chlorine is 35.4527. Okay, we said that isotopes have nice whole numbers. Where are those decimals coming from? So let's look at an example. This is something called average atomic weight. Okay, so average atomic weight, we'll use the example of chlorine. Chlorine has two naturally occurring isotopes, 35 and 37. I'm going to put all the numbers on here. 37 obviously is the heavier of the two options. Move this up a little bit, I guess. Okay, so this should have a mass of 35 AMUs, and this has a mass of 37 AMUs. Exactly nice whole numbers, no decimals at all. And what we find is that in nature, you end up with a mixture of these. And if it was exactly 50-50, the average would be 36. What we find is that in nature, this accounts for about 75.77%. And this is true whether it doesn't actually seem to matter where you get the chlorine from. If you got chlorine from the moon, or if you get it from, South America versus North America, like it's all about this distribution. And then you get about, what's the difference? 24.23% of this. And this is the naturally occurring distribution of these things. So what you do is you take the weighted average. So you take 0.7577 times 35, which is the weight. I guess I'll put units on it because I'm teaching you to be good at that, I guess. And then you're going to take 24.23% of 37 AMUs. And when you add that up, it comes out to 35.453, which is the number on the periodic table. So the idea is that anytime you're looking at the periodic table and you have all these numbers with decimals, like for antimony it's 121.760, there are no isotopes that weigh 121.760. But if you have billions of these, which is not uncommon, honestly, if you had like a pile of it that you could even see, there would probably be billions of them. The weighted average of all the naturally occurring isotopes is 121.760. Okay, so that's where this number comes from. We will use those decimal numbers a lot starting next chapter. For this chapter, for isotopes, ignore them. Okay. As far as the periodic table, we need to talk about some of the major divisions, like kind of the trends that are going on here. And honestly, it might just be easier to scribble all over a periodic table and show you how it works. So, the way I'm going to divide this little stair-step line divides metals and non-metals. It turns out, so I'm gonna make this more obvious, I guess. Okay, it turns out that anything that is this way, anything down and left of the stair-step line, are metals. I almost recommend, rather than memorizing that piece of information, just realize that this line divides metals and non-metals and pick something that you know is a metal and figure out which side of the line it's on. Like iron. Over here on this side, it is a metal. And it is on this side of the line, so all of these things over here are metals. Metals are not all exactly the same, but they do share some characteristics. Okay, so I'm gonna write all over this periodic table, I guess. So metals, they tend to be shiny. They tend to be solids. Mercury is the only exception in that category. So mercury is an exception. Okay, they tend to conduct heat. They conduct electricity. So if you go to your house and you take a hammer and knock out one of the walls and start ripping out power lines and pull off the little plastic conductor or plastic insulator, you'll find that it's hopefully made of metal inside your wires. Otherwise, your house is super weird. If you go in your kitchen and you go grab cookware, if you're gonna grab a pan and put it on the stove and start cooking like scrambled eggs or something, hopefully that pan is made of metal because metal conducts heat and then transfers it back to the food really quickly and easily. And anything on this side of the periodic table meets these qualifications. They also tend to be malleable. All that really means is if you hit it with a hammer for long enough and heat it up, it can be flattened into a sheet. Okay. They can also be ductile. What that means is if you heat it up and stretch it, it forms wires. Running out of space. They also tend to be cations if they form charges. They can be neutral. So if you pick up a piece of iron, it doesn't electrocute you because it doesn't have a charge. But it can have a charge, and if it does, it's probably going to be a positive charge. So, positive. Okay. Most of the periodic table is metals, actually. They are the most likely option as far as just distribution of things. Okay. Anything that is up and right of that stair-step line are non-metals. Non-metals don't really have a lot of similar characteristics. They kind of don't share, and they're all kind of unique. Some of them are gases, some of them are solids. Bromine is a liquid. They aren't really shiny necessarily, but maybe they are, some of them. They don't really conduct heat and electricity real well. They don't really form sheets and wires, but some of them might. The main characteristic that they share is that they tend to be anions, which means basically negative charges. That's about the only the only similarity between these. Okay, so this line divides those things. So metals tend to form positive charges, non-metals tend to form negative charges. Okay. Anything that is touching the line is something called a metalloid. So I'm going to write it kind of in between here. Metalloid. Trying to point at the arrow, or point at the line. Anything that is literally touching the line is a metalloid. So boron, aluminum, silicon, germanium, arsenic, antimony, tellurium, polonium, astatine, they all are metalloids. And what that means is they have some metallic properties and some non-metallic properties. So it's kind of a gradient. This looks like this really firm line in the sand, but honestly, it's anything that's touching it is going to behave a little weird. So like, for example, aluminum is shiny, it's a solid, it conducts heat. It actually kind of is terrible at conducting electricity, which is why it's not like a perfect metal. It forms sheets really easily. Obviously, you can buy aluminum foil. It can be made into wires, but it's really bad at it. Okay. Whereas if you compare this to like silicon, as far as non-metals, they just kind of don't do these things. It doesn't actually even form charges. It's happy to not have a charge in any way, shape, or form. So it doesn't really follow that rule. It's a solid. It doesn't conduct heat. It's actually used to resist conducting heat. You can buy silicon oven mitts, but it actually has electrical properties, which is why it's used in computer chips. Okay, it doesn't form sheets, doesn't form wires as well. It can be sort of made to act like wires, but it's not the typical definition of heating it up and stretching it out into wires. And since it doesn't form charges, it's not exactly a metal, but not exactly a non-metal either. So there's some gradient to this. A couple other things to point out on the periodic table since we got it here. You'll notice these little decimal numbers. There's a few that have little weird brackets around them, but most of them have decimals until you get up to 92, and then literally every single one has a parenthesis number, a nice whole number every time. I will tell you that anything above element 92 is fictional. What that means is if you went out with a shovel and walked all over the planet and started digging, you would never find anything from element 93 or above. Okay, they were made in particle accelerators and they're super, super unstable, which as far as I'm concerned means that we can ignore their existence. Plutonium is reasonably stable and we have a stockpile of it because we made it, but it's like the only one that is stable. So anytime you see on the news that somebody made element 116, I don't get excited about that. It's unimportant. Those are fictional elements. They don't matter. Okay, but that's why they have specific, they don't have decimals because there's only one naturally occurring isotope because we made them. Okay, all right, thank you.